Hey, YouTube, good morning. And class, good morning. I guess I should say just hey class, huh? Not YouTube, because I'm really not like a big YouTuber. So we've been working on hybridization, and I wanted to go ahead and make a video on that because I realized I thought I had one on there, but I don't. So let's go ahead and make that correction now. You will notice I'm not in my lab, that I'm at home, and this is kind of my little office, our sort of it's my office slash our kind of art room area. So over here we've got some stuff where we do some painting. I got some bookshelves with stuff, some reading material that's really near and dear to me. And then over here I have kind of my little area where I do some stuff. I do some writing. I do my my work that I do, personal computing and all that good stuff. Anyway, that's so now that I've given you a tour, and we wanted a world map, so we've got a world map kind of. Anyway, welcome to the office. So anyway, let's go ahead and jump in. As far as this video goes, there's a lot of stuff to it. There's going to be chapters down in the description where you can jump around to multiple examples. I recommend you watch as many of them as possible, just because if you're once you're first getting used to this information, it might be helpful to do that, to see as much variety as possible. But let's go ahead and start off with the concept of what this whole hybridization thing is in the first place. So so everything we know, it looks at the concept of energy and and everything is about energy. I don't care what it is you're doing. I don't care if we're talking about in biology, chemistry, physics, everything is always about energy. And energy, things are going to want to use the least amount of energy as possible. So this hybridization thing is all around that concept and this concept of Vesper theory that we've been talking about with bonding. All right. And so we know, like for instance, let's just take a methane atom. So for instance, we know methane is CH4, right? And so carbon we know has it wants to bond up to 4 times, and then we know a hydrogen atom has this one bond, this one electron right here that it can offer and share. And so we know that we could get a situation where hydrogen could go here, a hydrogen could share in that region, hydrogen could share in that region, and a hydrogen could share in this region right here is as well, right? And so we would get something that kind of looks like this, right? So there's methane, and we know from our 3D Vesper and stuff like that that we get something that kind of looks like this, right? This is our wow. That's pretty ugly. We get something that looks a little bit like this. We already know this. So if we take a look at carbon in its ground state, and we said ground state is where the atom is not energized, right? And so let's take a look at a carbon atom that is, I'm going to put GND for ground state. So I may just write ground, and my screensaver just went off. It's perfectly fine. I have a energy saving mode on it. So everything's always going to be from the perspective of what happens when it's at the ground state, at this lowest energy state, to something that causes it to become excited. And what's usually going to cause it to become excited is coming, it's in a system, so it's in an environment where something is pushing and pulling on it that causes a shift in electron density. So where the electrons are around the atom, the nuclear core of the atom, and that causes these sort of interactions. That's part of what causes some of these interactions to occur. All right, and so we know based on our periodic table that if we find carbon, we know that we have 1s2, 2s2, and then 2p2, right? So the 2p2 gets us to where carbon is. That's where our fourth electron in that second orbital is at, right? And so we have 1s, and there's two of those. Then we have 2s, and there's two of those. And then we'll come up here where we have 2p. Now remember, there's 3 spaces in the 2p, and we have 2 electrons in that second orbital. And now if we look at hydrogen, all right, so if we look at a hydrogen atom, and of course it's going to be in a ground state. It's always going to basically be in that ground state. So in the 1s orbital, there's only 1 electron that is available for hydrogen, right? So now, excuse me, if we think about it, a hydrogen, if it were to go in that first space right there, well, that takes care of one of those hydrogens. If this happened again and goes into that second space, well, that would take care of a second one. Now, if you think about it, and this came up in class the other day, and every once in a while this pops up without me having to ask it, and I was very pleased to see that this past week a couple of people actually intuitively saw this, which was very good. So that was wonderful to see. You're going to see that I'm going to change color here for a second because I'm trying to illuminate something. So let's think about this for a second. If we had, so technically we've already put 2 hydrogens, bonded 2 hydrogens in this. So we have 2 other hydrogens somewhere, right? We have 2 other hydrogens somewhere that want to bond on this. Well, it kind of looks like one would go into that place, yes. But there's only, and we know we can put 2 electrons in a space, that typically two electrons can occupy that particular region of space. Well, does it make sense that the 2 hydrogen atoms with each of their electrons would be in that one space? Because if that were the case, then what you would see is a carbon that has this hydrogen here, it has this hydrogen here, and then both of these hydrogens would kind of be in the same region of space. And that's not what we see happen. We know that that's not what occurs. And the molecule kits that we've been using, they show that they're sort of designed to represent what we know does happen. And so now we're sort of learning sort of in reverse order. We're sort of backwards engineering our understanding that there must be some sort of hybridization, some sort of combination of characteristics from our p and our s orbitals that are combining together, right? So think of what the concept of a hybrid is, right? So I'm going to, let me go ahead and clear this board here. All right, so we're back to where we were on this. So if some hybridization were to occur, some shifting of the electron density in various regions, then what we realize is we need 1, 2, 3, we need 4 regions of space where pairs of electrons can be, either where a bonding pair is, or bonding domain, or a lone pair where a non-bonding domain is at. There needs to be 4 in some way. In this case, there's 4 bonding domains. And so you can see that there is 1, 2, 3, 4 regions of space right here. So we need all 4 of those regions of space to kind of be together in such a way where the electrons can evenly distribute themselves, right? And if we think back to when we were first doing quantum numbers and some basics on quantum mechanics, we realized that the Aufbau principle, electrons will fill from the lowest orbitals, lowest energy states up, and then the Hund's rule, they're going to distribute as evenly as possible throughout all the spaces that are available before they double up, right? And so if we were to put 4 regions of space right here, and notice I'm coming down from where the P is, because some of the P's that are up here, they've come down a little bit, and this S has come up. All right, so now we have what is called an energized or an excited, right? It's energized, and so we call this the excited state. My handwriting is particularly not nicely done today. So we have the 1s. The 1s, nothing changed. Absolutely nothing changed in the 1s. And then with the 2s, so what is common between these is the 2. So all four of those electrons, they're in the same orbital region, but that orbital region we know is split up between a spherical s and an elongated sort of dumbbell-shaped p orbital. Now we have a hybrid, something that is showing characteristics of both. And if we think about it, we have one s, and then we have those three p's right there. So 1 out of 4 of these is an s, and 3 out of 4 are p's. So if you think about it, it would be 25% s character and 75% p character. All right. I'm backing that up. Now we see that there are, let me do this, and there are 1, 2, 3, 4 electrons. So I'm going to put 1, 2, 3, 4 electrons. I have followed Hund's rule. The electrons are as evenly distributed as they can be before they double up. All right. Now let's think about this. If we go back to what we had before, a hydrogen in that space, and I noticed how the arrow goes down, and that's following the Pauli's exclusion principle, right? Where any two electrons that are orbiting the same region of space, they can't have the same spin. So there's two things here. So this represents half, this represents the other 1/2. So this would be a positive 1/2, negative 1/2, right? And so now that's 1, 2, 3, 4. So all 4 of them, right, are 1 is going to into each of those spaces. So if we think about it, then this right here would represent our carbon hydrogen bonding sites. Okay. That was a lot. I need some coffee. So minus all this highlighting stuff right here, what you see here, so let me back all that up for you. If I back that up, I get rid of all this stuff right here. So let me put that back. That right there would represent what we would do. Okay, everything minus drawing the molecules. Although we could draw the molecules to the side if you were asked, or you're probably going to be asked to do that on some sort of assessment, or if you're thinking about it. But this would represent what we would do for methane to show the hybridization state that occurs so that the molecule can actually exist. All right. Let's go take a look. Oh, I forgot one of the most important parts. I must not. We see that there is one S. Out of all of this here, we see that there is an S. And then we see there are 3 P's, right? So there is the S. And then there's 1, 2, 3 P's. So this literally is called sp3. So we would say that this is sp3 hybridized. So this is an sp3 hybridization process that occurs, right? This is what we call sp3. All right, let's move on to another example and take a look and see what we can get. All right, so for this next example, let's look at something called Ethyne. So, you see Y and E, so that would mean it's a triple bonded carbon. And so methane, ethane, propane, etc. So ethane, so there's 2, right? There's 2 carbons. That's what that prefix, the eth part, means. So we know that this is 2 carbons that are triple bonded, and then it's a hydrocarbon. So we could also, the molecular name for this would be dicarbon dihydride, right? That would be another name, another way of naming it. So that's something that you're familiar with. Even if you don't understand hydrocarbon namings, then dicarbon dihydride would definitely be recognizable. Okay. So in this, what we need to do is take a look at what is happening where we have more than one bond. So here we have triple bonds. So I've skipped and gone straight to something with triple bonds. Let's just jump into this and see what happens. Remember, the hybridization states have to work for what's happening with the bonding. When we're done, it has to make sense. What you need to realize is there's going to be some hybridization that occurs. So automatically jump in and hybridize everything. One of the things you want to look for is this concept of whether or not it's sp3 or not, right? So here's an easy way to do that. So you'll remember we had our methane. And the way to, what you need to remember is this, is that there are, sorry about that, is there are 1, 2, 3, there are 4 regions of space where we have s and p orbitals that are where the valence electrons are, right? And so those 4 regions of space, if you think about it, when we had this, we called this sp3. So notice that the 3 here, and there's an understood 1 there. So 3 plus 1 is 4. And so notice we had 1, 2, 3, 4 bonding domains here. We had 4 domains. So what you're going to do is you're always going to take a look and ask yourself, how many domains, how many regions of space are there around the atom in which we're looking at? So if you think about it, there's a region of space right here between that carbon and hydrogen, and there's a region of space right there between the carbon and the carbon. So there's 2 regions of space. So what we would say is that this, sorry about that, what we would say is this carbon right here is what we call sp-hybridized, all right? So since there's only 2 regions of space, only those 2 regions are what hybridize, all right? That's how you approach every single one of these type of problems. So that would mean this carbon right here would also have to be sp hybridized. We're not going to hybridize hydrogen. It only has 1 valence electron. Doesn't need to hybridize. It can't hybridize to pull in any extra electrons. So that's never going to be anything you have to worry about anyway, right? All right, put that coffee back for now. All right, so let's go ahead and get our hybridized state for the carbon atom. And so we need the carbon atom to be in its excited state. All right, so we've got 1s, and of course the 1s, nothing is changing. We know there's 2 electrons in that first orbital. And so we take a look at this and we realize, okay, sp, so that's 2 hybridized pieces that have to occur. So there's this one here. I'll be consistent. I think I've been using yellow for that first one, so I will do that. So there has to be, the S would come up, and there's 1 S and 1 P. So if you think about it, there's 2 hybridized orbitals, and half of it is S and half of it is P. That's really kind of 50-50. So I'm going to come halfway between the S and the P here, and that's where I'm going to draw it. I'm going to draw 1, 2 spaces, okay? So that means that one of these, oops, I didn't mean to erase that. That means that one of these came down, and then that's your S that came up. And so now if you think about it, the other 2 are still up here. Now there are still 4 electrons, 2 in the 2s and 2 in the 2p. But now that there's hybridization has occurred, it's like another layer. There's a region within that region that now sort of exists. The electron density has been redistributed. And so we have to show 1, 2, 3, 4. We're following Hund's rule, where we are evenly distributing electrons within a region of space before we double them up, right? So we have successfully done that. Then, of course, we have hydrogen. So a hydrogen atom, and so we just need to show the ground state once again. And let me bring that down. I'm trying to be consistent here for you. So we have a 1s, and then there's that 1 valence electron that it has. Okay, so we, let me tell you what I'm going to do. I'm going to resize this for you. And the reason I'm going to resize it is so that when I'm getting ready to do, I'll have a little more real estate, screen real estate on the example to work with, so that as I'm working with stuff, it won't be so cramped. You can see a little bit better. All right. So I'm going to get rid of these highlights here because I don't want it to interfere with what we are working on, but you understand what's what. All right. So right now, carbon, hydrogen, and so a hydrogen could bond to right there, correct? And so that's taken care of. And then there's this carbon-carbon bond, and so another carbon atom from somewhere off over here that is hybridized the same way as this, what it does is it comes over here and it bonds to right there, okay? And that makes some sense. So it takes care of those two right there. All right, so now I'm going to remove this part right here because I don't want that there. I don't want that in the way of what I'm going to be writing. All right, so we know that right here we could say, just pick one, we could say that one of these is the carbon-carbon bonding site, because that's typically going to happen first. All right, and then right here is the carbon-hydrogen bonding site. So now the question is what's up with these two things right here, these two empty spaces? Well, if you think about it, we have a space right here where there needs to be some bonding between carbon and carbon. And so that space right there is available because remember, this is still the carbon atom. Okay. And now I'm going to pick a different color. I like purple. I like purple. So now I'm going to if I put this purple here, well, that doesn't show up well on the black background. I'm just going to go with green. That contrasts well enough. And so you can see that right there is that one. So if you think about it, the two that are up here still in the P, they didn't come down, so they didn't hybridize. So we know that this right here is where our unhybridized electrons are. So these two P regions, you could think of it as like a PX and a PY. They did not. They stayed unhybridized, right? And that would represent that's where those second and third bonds are. So there's a term we have for this. Okay. I don't know why I keep doing that. The very first bond that ever occurs, we refer to that as a sigma bond, and we write that using that little sigma symbol. So both of those right there we refer to as a sigma. All right. So, and then the other bonds that occur, we think of those as what's called a pi bond. All right. And so there was a pi bond that formed here and a pi bond that formed right there. All right. And so, I don't know, that looks pretty good. That looks pretty good. That looks pretty good. That now, so we know that this carbon atom excited state works because we have a bond between the carbon and hydrogen and the carbon and carbon that initially form, even if we didn't know the concept of what a sigma bond is. They initially formed, and then there still had to be some electrons that are sharing that space. And so these unhybridized regions of space where pi bonds form like this overlapping. So what happens is the electrons are sort of pulsating both top and bottom. They are overlapping in a region of space back and forth. So They're sort of vibrating and moving and back and forth, back and forth, back and forth, back and forth, back and forth into that space. All right. There's like a shared overlap. That's one way to kind of talk about these things. But you can see from the way that we drew the hybridized states that everything is in its proper place and works for the VSEPR structure that we have, right? I don't know. I kind of like that. Let's draw a spatial model of this so we can kind of see what that might look like. So taking a look at a spatial model, what we want to do is we've got carbon that we know is bonded to another carbon atom, right? And let me go ahead and resize this. So right now, that let me keep consistent with my colors. That bond right there is that right there. We can see there's a hydrogen bond on the same axis, horizontal. So there's a carbon to a hydrogen, and I'm drawing it spherically because we know the hydrogen and the one electron in its 1s, that's a spherical, takes on that spherical shape. So there's that bond. Again, both of those are sigma bonds. They're the first bonds that form. And then we have this bond right here, this carbon-hydrogen bond. So I'm going to do the same thing. Remember, this carbon is hybridized, so it has some P character. That's why I'm drawing it sort of elongated. And then, of course, we've got that right there. And then there's our hydrogen. There's that bond. Now we've got these two other bonds that are there, the second and the third bond, that doubled and tripled bond region. So I'm going to need multiple colors here. Let's go ahead and let's do that right there. So let's go with this bond right here. And it's easy. We'll just sort of draw that, draw that. And what I'm doing is it's on a different axis. All right. And so let me oops, I gotta actually choose the highlighter. So that's there, that's there, that's there, that's there. Okay. And now it's overlapping back and forth, moving back and forth. So we need to show this movement occurring. So I'm going to do that by kind of showing that. Oops, that's really not, I didn't really do a good job of that. Let me try that again. Kind of a little bit of a curving action to it. All right. And then we have one more. We have to work with this one right there. Okay. And so we need to represent that. So if you think about this, along here, we have like X and Y. So the next thing to do would be to look at a Z, all right? So I want to kind of go in this direction, angled like this. I want to go angled like this. And you can kind of see where we're going with this, hopefully. I think you do. So I'm going to draw this like that, draw this like that. I'm going to do the same with this here and the same here. And we need a different color. We're going with green. I'm hoping the green will work for what I want to do. There's the green, there's the green, there's the green, there's the green, and this green, you can see here, see how I'm drawing this? You can kind of see now that Z, it makes it look like it's on this sort of plane going like this, as opposed to this right here. So this is a pi bond, and this is a pi bond. So there's not, so Everything that's blue is one pi bond. Everything that's green is one pi bond. Remember, it's overlapping on this axis, and it's overlapping on this axis, back and forth, back and forth, back and forth, back and forth. So this would represent what we call a spatial model. All right, sort of modeling how things are taking up three-dimensional space. And so you're going to want to be responsible for, you're going to want to be able to do this for every single molecule that we're going to be studying. I like that. So yeah, remember, sigma bond, and then we have right here, these are the pi bonds for a molecule. So far, so good. I like this. This is good. Let's look at another example. We're already familiar with carbon dioxide. So we've got carbon dioxide. Ground state. Energy going up. We will need the carbon atom in its ground state. Wow, that's pretty bad. We know we're going to need a hybridized carbon, so let's just go ahead and jump in to do that. That's Macy in the background. Not sure if you can hear it, but I can hear it. So here's the excited state. Of course, 1s doesn't get affected, doesn't hybridize. Go back to what I've taught you. If you think about it, there's a region of space here and there's a region of space here. Two regions of space. So with that said, that means that this carbon is sp-hybridized. There's two regions of space. Both the exponents on the 1 and the 1 on the s and the p add up to 2. All right. So that means we need sp2 for this. So I'm going to bring the s up and bring one of the p's down. And since there's two spaces, that's 50-50. I'm going to go about halfway. Okay. So we know that would be sp2 hybridized. So there would be two of those p's still up there, and there's a total of 1, 2, 3, 4 electrons, right? 4 electrons. So the carbon is done. So now the question is let's take a look at oxygen. Well, now we have a situation where we have multiple atoms that probably are going to be hybridizing, because if you think about it, this oxygen has 1, 2, 3 regions of space around it. Well, that sounds a whole lot like it should be sp1, 2, right? sp2, because the 2 plus the 1 equals 3. There's those 3 regions of space. So we need 1s and 2 p's. All right. So first we need the ground state for oxygen. It's always a good place to start. And we're going to go with the ground state. I'm just not writing the word state just to save time and space. So we've got 1s. Now let's go back to our periodic table in case you've forgotten. We see oxygen. The last electron would be in 2p4, right? So there's a total of 6 electrons in the second orbital for oxygen. 2 of them are in the 2s, and 2 of them are in the 2p. In the 2p, right? There's 4 of them are in the 2p. So we need to go back. So we've got 2s. There's 1, 2. We come up here to where the 2p is. Remember, this is still oxygen. 1, 2, 3, and we've got 1, 2, 3, 4 in the 2p, right? Let me move this down here out of the way because I'm going to need some of that space up there in just a second. So now we need our excited oxygen. All right. So the 1s, again, nothing's happening with the 1s. And we said it was sp2. So we need to bring up 1s and 2p. So that's closer to the p, right? So it would be 1/3, 33% s character, 2/3, about 67% p character, right? So I'm going to go, so halfway, you know, I'm going to go above the halfway. So I'm going to go up a little bit higher, and I'm going to put 1, 2, 3. Now we see that there is a total of 1, 2, 3, 4, 5, 6 electrons. So I need to spread those 6 electrons out. Now remember, we had 2 of the p's come down, so one of the p's is still, it's still up there, right? So now we spread this out. So this right here is sp2, and here is the 2. Oh, that's really bad. Here is the 2p. So there's 6 electrons. 1, 2, 3, 4. Hundred roll, I've spread everything out, right? And then we go 5, 6. Okay. All right, so now we ask ourselves, is this going to work for what we're doing? So let me put a little bit of space between these two. I got them a little bit close. I'm just trying to get everything on here and aligned as much as possible. So let's think about this for a second. If we look at the carbon atom, and I'm going to, let's see, get rid of that. Oh, let me erase this and clean it up completely so that I can do this for you. All right. The carbon is bonded to the oxygen atom. We know that that's going to create a sigma bond. We know that. All right. So let's see if what we have works. So we need a carbon atom that's going to bond to an oxygen atom. Well, if you think about it, the carbon atom right here and the oxygen atom right there, well, that could fit what I have highlighted yellow. Well, that seems to work because we have hybridized orbitals that are doing that, right? And then if we look at the fact that the carbon atom has a second bond, so it's double bonded, so that must mean that there is a space that is unhybridized. Well, right there is an unhybridized space. So that seems to work. Got it. So now if you think about it, we could repeat that with the other oxygen atom that's doing the exact same thing. We would have one bonded sigma bond. Then we have another unhybridized region for the double bond. So far that takes care of the bonds. Then that's good to go. So that takes care of all of those. That would take care of this and this for the next set of bonds. So now we go back to the oxygen and we ask ourselves, hang on a second. There is a lone pair here and a lone pair here. Well, if you think about it, there's a pair of electrons here, and there's a pair of electrons here on this excited oxygen atom. We've included those pair of electrons, those lone pairs, when we were deciding if it was sp2, saying those are hybridized regions. And notice the 2 pair of electrons are in the hybridized regions of space, right? And so so the question is, well, what's up with this? Well, when we were doing this over here for carbon, that's a carbon-oxygen unhybridized bond. So right there, that's what that is. The unhybridized areas are overlapping next to each other. So you can see that if I had another hybridized oxygen, that the same thing would happen to this one here with the other unhybridized oxygen space right there with that one, right? Hopefully that helps. Hopefully you're seeing that. If not, build your molecule. Maybe that could help. I might do a video where I build a molecule and do that if people want. I just wanted to, this video is already 43 minutes long, but remember there's gonna be chapter titles. But stuff like this can't just be distilled down to 5 or 10 minutes. If everything were that easy in life, we'd all be walking around geniuses. We'd already figured out space travel and whatever. Okay. All right. So I don't know. I was gonna do another one. Oops, that was a good catch. I was gonna do another one, but I think what I might do is save that one and one other for another video at some other time. If someone requests it, what I'll do is I'll just chapter this part out. I do want to leave you with one last thing though. This will only take a second. Let's summarize this. We've seen that we can have sp3 and sp2 and sp. So let's summarize this. So we've got energy, right? And we always show it in an increasing fashion. Okay, so we've got energy, and then so we've got our 1s, and I know I've only stuck with like 2s and 2p, but if you get some larger atoms, this could be happening in the 3s and 3p. This occurs wherever it is. Right? And then we've got 2s, and then we've got 2p. So if we have a hybridized state of an atom, then whichever atom it happens to be, then that 1s we know is not affected. So, but we know that at least the 2s always has to come up. It always has to come up. So the 2s is going to be somewhere. So the first thing we ever saw was was sp3. So sp3. So the s came up, and then all three p orbitals come down. Well, there could also be a state, as we've seen. The 1s is not affected, but then the s comes up, but only two of the p's come down. So that would be sp2, 1s and two of the p's, and the other 2p is still up there. Notice I'm showing that above sp3 because it's at a higher energy state. And then there is another where we could take the 1s and only and where the 2s is, that 2s comes up and only one of the p's comes down, and that would be approximately halfway, and we could call that sp. So that means the other two p orbitals are still up there. So I can go ahead and put 2p here and 2p here. So these represent the three sort of hybridization states. All right, these are your three hybridization states, so to speak: sp3, sp2, and sp. It's going to hybridize. And then at that point, remember, you just follow. So that follows the Aufbau principle, where you fill from the lower energy levels up, and then Hund's rule. Electron density is going to be distributed in such a way where every space has at least one electron before it doubles up. And then we would worry about Pauli's exclusion principle, where the electrons spin in an opposite direction, which we would call the negative 1/2 direction. Whew, that's a lot. Macy, you ready to go for a walk? Ready to go for a run? All right, so while this video is processing, I'm going to take Macy and we're going to go for a walk, and then we're going to go run. This is our typical thing. Twice a week, we go for a walk, and then, we go for a walk almost every day, but then twice a week, we'll go for a run. So today, and Macy's really excited about this, aren't you, Macy? Yeah, she's just laying there. She's not excited yet, but she's going to be. She's about to go run about a mile or so. She's going to love it. And that caffeine to get me going. Hope this enjoyed. Hope you enjoyed this. I hope this was helpful. And then, if not, leave a comment, and I'll be happy to answer any questions. If you've got any more, if anything else pops up, or if you have an idea about something else, please feel free to drop a comment and ask. Or if you're in my class, ask me in class, or a little of both. Hope you have a good day. Hope this helped, and I will see you all soon, either live in person or virtually.